this is definitely going to be a game-changing piece of machines. Nomad was really a hack to get things working faster. Flaps was very easy to operate and scale and manage because it had no database. So this is the GitHub repo. It's used for hiring clearly because all of the tests have been removed. Let's say the FSM failed and it wasn't going to finish. We needed to clean stuff up. FlyD is now stopped. We're updating the code. We're starting it back up. Let's say we wanted to add another transition or delete one. That could wreak havoc. Probably from the outside as a customer of Fly, hopefully it looks like a very simple system.
Many months ago, I read a Fly.io blog post that I really enjoyed from start to finish. And the title was The Exit Interview, JP Phillips. And the blog post was so good that I felt compelled to reach out to JP and see if you'd be interested to share more than a glimpse into what I consider to be an amazing piece of infrastructure that runs at a global scale. JP, welcome to Make It Work.
Thanks. I'm really excited to be here. You know, when I agreed to do the exit interview as a blog post, I was a little apprehensive just because I know the audience that Fly had. They were known for really good posts, right? Thomas is a great writer. Kurt is a great writer. We always like to lift the curtain up whenever we could. And this was just another form of that, but not as technical. And I was very appreciative of just the opportunity to do it as well. Because a lot of times exit interviews are they're just procedural, right? It's the company checking the boxes. And in true Fly fashion, this was more of no, we're going to talk about this, have this a little more openly and give an opportunity to just reflect and disagree, talk about where things went well and where things went wrong. And it was really cool. And I guess the feedback from it has always been really great, right? I mean, it's it's always a lot of people are still surprised that it happened, which, I think looking back, I still am to some degree. I was really, really excited, when you reached out. I always love hearing from customers as well. If you hang out on the community forums for too long, several years ago, it was hard to work some days, right? Because it's just gosh, we're just not doing anything well, even though largely we were. Didn't always feel like that. And so it's one of my favorite things was working there, was being able to connect with customers more direct or even indirectly, and just hear about their experiences and just the cool things that they've been able to do with the platform.
The reason why this blog post specifically spoke to me, I mean, there were many others that I read, as you mentioned, some deep technical ones. I remember when Nomad was being replaced and FlyD came about. That was an amazing deep dive. Kurt with his 5-hour CDN. I mean, that one was a little bit technical, but also had the human element and the fun element and what if elements. I really like that. But this specific one, It was the human element. I mean, you actually get to meet the human behind a piece of technology that I think is impressive. So that was, I think it was about a year ago when this blog post came out.
6 months, just over 6 months.
6
actually.
months.
Yeah.
Okay, 6 months.
It feels like a year. I'll agree with that. It feels like a year.
It was a long year for sure.
Yeah.
So since, in the last 6 months, have any of your thoughts changed because you had a little bit more time to maybe reflect on some of the things and internalize them better?
There was the original Machines product, and then, you could really only run one image. You couldn't run as, PID1. A lot of companies, so a lot of people were like, well, I need, they wanted the experience of a VM, but it wasn't quite really that because, you couldn't do typical things. And then with the AI, all the AI stuff that was coming out, it's these agents, they really just need to be able to kind of have control of things. And so when we started doing Pilot, which was the new init, we didn't really commit hard to it. And I really wish I would have pushed harder on that. Because I think Pilot as the underlying engine in the VM is really what is going to open up a whole new class of applications, deployment strategies, and just technology even, with how they build the VM. And because we had that over a year before I left, right? I mean, it was that. It was a longer drawn out project, which we don't typically do there. And so I wish we had really jumped headfirst into that and committed to almost like we did with when we said, all right, we're going to replace Nomad with Machines. It was a big effort. I kind of wish I would have had a little more foresight and a little more intuition to be like, okay, this is definitely going to be a game changing piece of machines. And I probably would have tried to really just get that done faster because it's out there now. I think it's going to be a big part of the product moving forward. So I think there's that one. And then the other one would be, even last night, so there's this, like most of you leave a company, a lot of times you'll stay in touch through various Slack groups. And so there's one for Fly, and there's still existing people. So Thomas, I think, manages the Slack, or he's one of the admins. And so there's some current and former Fly people in there, and we were talking. And of course, the SQLite versus BoltDB thing came up again, which was funny. And so I think if I were to do it again, I would maybe still do Bolt or SQLite, but I would want to build the flyD, the engine, to be a little more multi-tenant aware, right? So the way like flyD in general, when it's performing work, it's really focused on like one resource, like a volume or a machine, and that's at like the FSM level. But like above that, it's like everything is sort of like commingled. I think a very interesting design that is it's overlooked because it's not niche, but it's like it's probably maybe only 20%, 30% of the architectures could support it. But the idea would be it's like a database per tenant, and you decide what that tenant, whether that's a database per machine or like at Fly there's like the machine, the app, the org. On every host you could have some way of multi-tenancy, because the big push that I had with Bolt specifically over like SQLite was, I think I mentioned this in the post, I never lost really much sleep worried about somebody doing an analytical query in the middle of the night or like during the day, or running a command trying to alter data with the live system, right? It's like, I think that mentality it's understandable. It's like in a lot of ways, you have to have that ability. But if you can take that away, it kind of forces you to think very critical about like the operational aspect of the system and expose your observability really well, so that when you have something's going wrong and you need to understand like what's going on, you're not firing open a SQL shell to then start running a bunch of arbitrary commands to try to understand the system, because it requires deep knowledge of the system. You have to understand the schema, how things are put together. Versus with, when I went with Bolt, it really kind of meant like, okay, you can't touch the running database. And that was by design, because I really felt like it was important for me operationally. But if I were to do it again, I would either do, I would have some sort of tenancy. And I think you see this with databases like, I think it's Nile.dev. Yeah, Nile.dev. So they're basically approaching building the database as a multi-tenant system, because I do think it is a design pattern that is overlooked. And so I would probably do that a little different. I would still use Bolt, maybe SQLite, because you combine that with something like Lightstream or LightFS. Maybe you basically can make sure that you're also easily backing it up off site. And then if you need to do analytical stuff, you could pull in something like ClickHouse maybe. You've got all of it. Maybe you're shipping all your SQLites to S3, and if somebody needs to do like an analytical thing or like wants to investigate something, they're not doing it against the live system, right? I think I've personally had run commands in terminals that caused outages or incidents, and I think we can't prevent them, but I think ultimately we're just trying to like minimize the opportunity for them and limit the impact and limit the blast radius. And so for me, that was really what that was all about. And it didn't completely eliminate, issues, but to me, it just kind of took away a whole class of them. So I would build multi-tenancy into flyD better all the way down to the database level.
That's a very comprehensive answer. I mean, for those that maybe are not able to connect some of these very deep thoughts to like how this started, I would recommend maybe pausing this now, reading maybe the blog post, even if you've read it before, as a refresher. We will take a step back and we'll start from the top. The assumption is that you have built global systems, distributed systems that manage, I say, more than a process. There's a process, there's a VIA, there's a disk, there's some networking involved, and this is at a very large scale. We're talking, I would say, tens of thousands is too small, so more than tens of thousands.
Definitely,
And
yeah.
this is again worldwide.
Right.
There's no upper limit because the system, based on where you've seen it, just grows. But you
Hmm.
have to be with it through that growth and see it succeed and scale 100 times, 1,000
Right.
times, 1,000,000 times based on what it was before. So you were there from the beginning. You were there from the beginning of fly machines
Yep.
specifically.
Yep.
How did that idea start, fly machines? Like, what started the whole fly machines era?
My relationship with Kurt and Jerome, two of the co-founders, go back to a previous startup. It was Mongo HQ, Compose IO, managed database as a service, right? And so we learned a lot there running multi-tenancy systems. And then one of the things that I always knew was like you kind of have to run the app, right? And so Fly went through several iterations early on, and I'd stayed in touch with them all throughout. And I remember when they were building the first, like, I guess, Fly apps platform on Nomad. I had lots of fun conversations with Kurt about how they're doing that, and they were going to use Firecracker. And even when they did the initial like Fly apps, I think Kurt knew early on that like Nomad was really a hack to get things working faster. It's like we don't want to build that right now, right? We want to really focus on the Fly apps, the platform, the user experience, the global proxy, making sure that that works well and is resilient and performant. And took a shortcut, and you use Nomad because Nomad gives you a lot of the flexibility to run the workload in different isolation modes, right? You can use the default container one, or you can bring your own. And so they were able to make it work pretty well with running Nomad, but they didn't want the operational complexity of running multiple Nomad clusters either. And so they made the decision early on. It's like, we're going to have one Nomad. The agents will run everywhere, and we'll accept that operational risk. It's non-standard, but they made it, like, we made it work, and it worked really well for a long time. And so Kurt and I had been talking on and off probably for at least a year before I joined Fly about just running workloads, what that looks like. How would you do that if you didn't have a scheduler and a central orchestrator, right? Because you go back 10 years, you've got Mesos has hit the scene, and then Kubernetes. There was the one from CoreOS, and even Docker, I think, was trying to come up with some sort of like orchestration system. And ultimately, those systems are necessary, right? You have to have those, and they work really well. But then I think if you look at maybe like AWS and even Google Cloud, Fly's goal ultimately was to be a cloud provider, right? To provide these cloud primitives, and one of those is the compute. And when you come to like managing compute, a lot of times the scheduler and the orchestrator really kind of just get in the way beyond just that initial place the workload. And so what we talked about was like, okay, if we carve out the scheduler, what is it that we need to be responsible for? And that's where the idea of that the global API, which is, I think it's referred to as Flaps, it runs globally on every host and on every like gateway. And so what we decided was like, okay, if we carve out the scheduler, how simple can we make the scheduling logic such that it's fast, efficient, at scale, like regardless of the size of the platform, and then push down a lot of the hard work to these FlyD agents. When we did that, obviously we lost some things, right? So it's like if a host dies, we don't have a scheduler that's then going to go and reschedule those onto other systems. And so the idea with Fly Machines is it was really all about simplicity from the user's perspective. It did put more on the user, and that like, if you can't just have one machine, and if the host dies, like we're going to the machine would move for you. We knew that would be a thing that was needed, and eventually got there. But the whole thing with Fly Machines was like, you should be able to run a workload if you're in UK or if you're in Australia, and you can run that workload, and everything about running that is fast, and it doesn't have to dial back to Virginia, right? It's like, or even like some central orchestrator in APAC, right? You could have designed it such that you've got like regional nomads clusters, regional orchestrators. But again, then it's like that becomes extra operational overhead complexity. And so we felt like we could do it differently. We could carve out the scheduler. put that in the API. So Flaps, when it gets a request, it makes that quick scheduling decision and it places the workload. The original version, if it placed it and that failed, it was like, we're going to tell you it failed, right? And it's putting more kind of on the customer, but we try to do it in simple terms. It's like you create the machine and either that succeeds or it doesn't succeed. So yeah, and then I had been doing some stuff at HashiCorp with basically building a platform for running the HashiCorp products, and that was a lot of fun. But I think ultimately what I really wanted to get back to is being able to build a product that could just be usable by anyone. I love the idea of it being global. You can create a machine in Australia and APAC and Europe with like a curl command, right? I mean, that's just ultimately, I think that was the vision that Kurt pitched me on. I had some ideas of how I would want to do that coming in, but I wasn't, they weren't super solid. But thankfully, there had already been Jerome, the other co-founder, had done a sort of proof of concept. So I was able to sort of see what he was thinking and merge that with what I was thinking. And we ultimately ended up with like a fly-D and how it works more or less still today, which is, just pretty great. We got some things wrong. We learned some things, but yeah, the idea of you can run a curl command or a CLI command, and your workload is immediately running in one region or 10 regions. It should be that simple, really, for the compute, right? And having done different forms of compute prior to that, it just seemed like it opened up, a whole new possibility for how companies can build their products, how you can not worry about the complexity of managing your system, right? You think about like the day two operations and stuff like that. It's like you shouldn't have to worry about that kind of stuff. You shouldn't have to worry about networking, and you should just be able to like deploy your compute workload, and it should really just kind of work and be pretty easy to do. So yeah, so it's kind of a long form way that I think we got there, but I think Kurt pitched me really well on the vision, and I think what you see today is actually a really good result of that vision, combined with just like the history of running different forms of compute that I've had.
In terms of secret ingredients that made this possible, I've heard keeping it simple, having something that is easy to explain and understand, which has as few moving components as possible. The one thing which I've heard, and I would love to double click on that, is we have as few centralized points as possible, because once you centralize any sort of state, the complexities associated with that are very high and often underestimated. And the fourth thing, I haven't heard anything about the iteration. So it seems like from the beginning, you kind of got the initial design right, in the sense that it didn't need any major reworkings. So maybe like, was that the experience? Was that the simplicity? I'm sure a combination of the two, but I still can't believe there were like no major changes to the system from the initial version. How is that possible?
Yeah, so I mean, we took shortcuts obviously early on with like some parts of placing the workload still had to call back to the central API, right? It's like we knew we couldn't replace because the data, like some of the data still lived, in Virginia, only accessible through the GraphQL API. And so early on, we were like, okay, we'll deal with that later. So that was one piece where it's like that we knew that was an operational risk, or that was a, complexity that we had to have, and a latency as well. Above fly-D, we kind of had to make some changes over time. And then within fly-D, so the very first version of it only knew how to manage machines, but we also had the volumes resource. There was like a whole separate process that was running volumes. And so when so I built this first, like what we call the FSM, Finite State Machine in fly-D for managing machines. It seemed like it was going to work well. And so shortly after that, two things happened, I think pretty close together. Like that was working well. We were having some issues with, the reliability of creating a volume. And Go, which is what fly-D is written in, had released generics. And I'd been keeping an eye on it and tried it a few ways. And so Kurt, I think, was like, hey, it would be great if like fly-D could also just manage volumes, because ultimately, again, it's like less things to manage. Like we don't need a process on the host managing volumes and a process for managing machines, like it should really just be the one thing. And so we had an iteration where, okay, rebuilt the FSM, used generics to basically make it to be able to, the idea is that it's resource agnostic. It didn't really care about what it was. It was, managing the state of. And then above flyD though, so the original design between flaps, which is it's just it's an API, also written in Go, it talked to flyD via NATS. So NATS is great, right? It's a really cool technology. It can do RPC type patterns. The way we ran it Fly, again, we basically had a global, like a super cluster, right? It's like, again, the design of Fly was like, you could, if a request hits, Virginia and your machine is in UK, we should just easily be able to route there without a lot of overhead or complexity. And so we did the same thing with NATS, the NATS cluster. And so the way it worked would be flaps would use NATS RPC protocol to basically send a message to flyD, and then it would, wait for it to come back. We had some issues with that over time, right? Messages would just get dropped. And I think that is the nature of NATS when you're not using it in, I believe it's called Jetstream mode, where it actually persists things. Because again, that would have just added an operational complexity. We didn't want to be managing state in that regard. And so one of the first things I did want to improve about that architecture is I wanted to get rid of NATS, and flaps can talk to flyD directly. And so what we did is we swapped out NATS, and so flyD exposes a connect RPC API similar to gRPC, but I don't know if you're familiar with Connect. It came out of the company Buff that created the Buff CLI, and they have the Buff registry. Well, they also came out with Connect RPC, and I liked it, the semantics of it better than just raw gRPC. So we had flyD expose an API, and then flaps could, again, because of the WireGuard network that was in place there, every flaps could talk to every flyD. And so it made it more reliable from when flaps sends a request, it's TCP, it is stateful request. If it fails, we can at least bubble that back up faster. And more importantly, when it came to the placement decision, the way we had to do that one, it was basically like, okay, we know we need to place a machine in, we'll say London, right? And so flaps would then broadcast out a NATS message on a topic that all of the flyDs in London would hopefully get, and flyDs would hopefully, would send back a response, and flaps would hopefully get it. But basically flaps, it would have to wait. It says, all right, I sent 10 messages, I should get back 10 responses. So I'm going to wait. And it's like, okay, if I get 8 of them back within 100 milliseconds, maybe that's fine. And I'll just continue on. And if I get 2 more messages later, too bad, you were too slow. But it could be that those hosts might actually be the best place for this machine. So we had some issues there with just the reliability of messages. And so when we flipped it, it was basically flaps would be I can, fan out an API call to these hosts, to the flyDs, and they immediately give me back their, capacity information. I can compute the scoring. I can make that placement decision right away. And we definitely saw an improvement there of reliability. The other component that was not there in the beginning that we, I think, had by this point was corrosion. So corrosion it's one of the Fly has open sourced it. It's a really amazing piece of technology, and it unblocked a lot of architectural decisions that we made. Because again, when you go back to that, how do you access the state? Typical setups, you have a database cluster running somewhere. Everything makes a connection to that database to run the queries and get it back. And so you've got in agents or in processes connecting back to one cluster. Typically, if you've got something like Cockroach, maybe you have a little bit more complicated because you've got geo replication stuff, or Vitesse, right? But we didn't want, again, that's operational complexity. And so what corrosion gave us was flyD was the source of truth for the state, right? It knew everything about machines and everything about volumes. How do we get that data? How do we share it? Right? It's how do you share this information to flaps, to other systems? And so corrosion was that answer. And so the way it worked was flyD, as it was basically running its finite state machines, it would also update corrosion. So corrosion is it ran on every host, and so corrosion would see this like it would just be a SQLite, right? Insert corrosion would propagate that out through the rest of the network, and it would do it within region and within like nearby regions. You're talking less than a second, typically, like easily less than a second, and then globally, its ability to replicate, a change globally within, we'll say like probably 5 seconds if I had to guess, from what I remember. And so what that gave us was like in the Flaps API, it could then just do SQLite queries to get information about the machine, to figure out, okay, I need to create a machine in London. I can quickly do a query to like get the address of all flyDs that have reported as up in the last however long, and then it can quickly make those API calls, get them back. So to me, I think corrosion is what really unlocked a lot of reliability improvements. That took some time, right? Because like there was a version 1 of corrosion, just like there was a version 1 kind of like flyD. There became a version 2 of corrosion, learning, and then flyD evolved over time. It largely stayed the same, but like the FSM stuff evolved, the API that exposed evolved. And so I think what the best thing that we got right, that they had already, before I joined, they had really learned was like the WireGuard network is the basically point to point, easy, network isolation within an app. And then the Firecracker story, and just how we, could use Firecracker to pretty as securely as, I think you can, for the most part, run multi-tenant workloads, but do it from a Docker image. I think that was probably the thing that they got right that never changed. And then from that, like that decision, everything grew from that. And I think that'll probably even change at some point, because we learned a lot with Docker, like not everybody's images are well formed, right? Some of them are very large, and so you have that overhead of downloading the image and unpacking it and all of that. So that, I think that there's some improvements to be had there. But ultimately, that was the thing that never changed for the most part. It's like the only thing that changed maybe before I left was with Pilot, you could run more than one image, right? You could actually we had the container-based init, which is really cool. So if I had to think about the things that really changed, from like the initial release of machines, whatever year that was, to like when I left, it was corrosion, and they unlocked just a lot of design decisions that really enabled that no central orchestrator, no central state. We could share the state across region and globally when we needed to. And it just, it made things, I think, in a lot of ways simple, because it's like Flaps can be pretty dumb. It had no data. It didn't have a database itself. It only relied on like corrosion, or it would have to call externally for anything else.
That's a really interesting story. I really like how you need to make the little course corrections as you're building this thing, because stuff is happening. You have to pay attention to that. The scale increases as you're making these things, by the way, so it's never fixed.
Right.
You have the Heisenbugs that only happen in production, nowhere else. Good luck reproducing that.
Yes.
So how do you first of all like capture it, and then understand like, okay, so what just happened? How do I mitigate this in the future? I mean, I'm sure that must have taken a while. But there are two things which I know are critical components that every single user gets to use them. I would say they're the most important ones. There's a couple others, but these two, I think they're really important. I know that one of them is very important to you. SQLite versus BoltDB. You mentioned it at the beginning, so I would like us to just deep dive a little bit into that and what it means for Flaps and flyD. Mm-hmm. And the other one is the fly-proxy, which that thing is just massive. It needs to handle so many requests because, okay, great, you have like all these Firecracker VMs, you have all these hosts, but what happens in front? And the fly-proxy is such a critical piece of infrastructure. Everything can be perfect in Flaps and flyD. If fly-proxy doesn't work, nothing works, really.
Correct. Everybody knows.
Exactly. So we can deep dive into whichever one you want
Okay.
first,
Yeah,
but
yeah.
these are the two which are on my list next.
Yeah, so the SQLite and BoltDB, I think whenever I think about that, for me, it's like, for whatever reason, I think my mind, the way it works, I like to think about things in a I guess more of like a key value type design, right? It's like I have a machine, I'm just thinking about that machine. It might have like several versions. The version is really just, another key. And then I have the data. And I never really, when fly-D was being built and still runs today, it largely, when it's doing an action, it's only like when it starts an FSM or is managing a resource, it only cares about that one resource. So it doesn't need all the features of SQL, right? It's like SQL is just chock full of, the query language is amazing. The things that the way you can get the data and query the data, right? It's a very good human tool, I would say. I don't know that it's a very good computer tool. Like, I don't think computers want to be parsing SQL and running SQL. I think that they actually would much prefer just like, here's a key, here's a file, and here's your data. And so that's why I think when I was designing fly-D, it was like, I really just want to be like, here's your machine, here's your data. This may not be right or true, but for me, it was like, if I don't have SQL available to me, I actually think the system itself can be simpler. Because if I did have SQL, I would be like, oh, I could just do this, or I could run this query and I can have, it's going to make my schema is going to be like this. And it's like, okay, yeah, it absolutely could do that. It would work both ways. There's multiple right answers. You choose the best one given the context at the time. For me, given how I had been thinking about fly-D and wanted fly-D to operate, BoltDB just naturally made sense for me. I guess I had experience using it. I'd seen it in production systems, and ultimately SQLite, it has no real permissions. Is the other one, right? I sort of alluded to this earlier, but it's like, okay, if fly-D is running happily and it's connected to a SQLite or even in SQLites, anybody can just if they can get to the host, they can access the database and they can run queries. They can run, and there's no like you can run selects, you can run updates, you can run deletes, and if somebody were to do that, a few things could happen. One, flight, like it run in like an analytical query that could really slow the system down, and then that would be noticeable to customers. They could accidentally run an update or a delete command, thinking they were in one terminal when they were really on a different terminal, and that could just you could say it's recoverable because you can do the light stream backups and LightFS, but ultimately, like you're creating opportunities for just disaster in a lot of ways. And so one of the things that I also like about Bolt, and it really just the embedded databases like Bolt, is that once the process starts, like you can't even connect, you can't even open the file for reading, right? It basically prevents. I mean, you can modify, you can obviously corrupt a file, but if you were to like write a program to open it, it wouldn't give you access, because as soon as the file is opened, nothing else can touch it. And just for me, I just really loved that simplicity. I love that design of like, I don't ever have to worry about myself making a mistake, much less anyone else, because I've made them multiple times. Now, if I, say, all right, could I have done it differently and said, okay, how could you, I would definitely have, if it was like, edict, everything is SQLite, that's fine. We'll figure out, how to deal with the schema migration. And I would probably be like, but we absolutely cannot have just like one SQLite file for the whole system. I would want some form of database multi-tenancy, such that, yeah, if you want to, connect, if you need to get on the host and you want to analyze or, see what's going on, and you want to do it with SQL queries, that's fine. You'll have to know like which database to go poke in. You'll have to know the schema. Versus what we ultimately ended up with fly-D and using Bolt. fly-D exposed a CLI, And so if you needed to see like, okay, show me the machines on the host, show me the volumes, let me get information about the machine, there was a CLI command. And so again, it's like flyD is the thing that really knows the state of the system, how the data is in the database, and how it can be presented. Let's put a CLI/API on top of that, so that if you need to inspect the system, you do it through flyD versus through the database, right? And that's just that's just me. It's more of like, if I think back all the way to when I first started working, I made mistakes because I was connected to the database, and I made other people's lives miserable because I was connected to the database. It's not that I don't think that that should not be allowed or should like it's terrible design. It's like, no, you have like normal systems, you're going to have a normal database that you can probably connect to. But for flyD, for this agent, that really no one should ever be touching the database is kind of how I felt about it. And I still felt that way even when I left. I was like, I it's not that I didn't understand the need to be able to introspect the system. It was that I fundamentally did not agree with doing it by connecting to the database.
What about flaps? Do you think that flaps, I mean, I'm not sure if it was using any sort of database.
Nope. Flaps was completely stateless. No, it booted up.
So easy then.
Right. And so again, it's like, we had talked about it at one point. It's like, well, should flaps have a database? And I'm like, no, I don't want it to. It had, because we had corrosion, it could rely on corrosion. And we had some other mechanisms where it's like, okay, if worst comes to worst, it could like call back to like some other system to get information that it didn't have. And that would be like, yeah, that's your worst case scenario. But ultimately, what made flaps easy to operate and scale and deploy was that it was completely stateless. Like, it started up, if it needed any information, it would get it from corrosion, or it would ask flyD for the information. If it did, I don't even know that we did a lot of in-memory caching. I know we did some, because it's like, once we knew a machine was on a certain host, we didn't need to like requery corrosion to get the address to make that API call. It's like, okay, we can easily, skip that SQL query, but that's a, minor optimization, I would say. And even that, it was just not that, again, it was just not that complex, I don't feel like. And
Yeah.
for flaps, SQLite made perfect sense, right? We knew like it needed to do more SQL query. Like, it needed to be able to aggregate data across the system. flyD never needed to aggregate data, because all it cared about was really one machine at a time, or one volume. When it was actually doing work, it didn't need to do any like aggregations or joining or anything like that. It was like everything it needed to know about the resource was in a record, which again still would work with SQLite. But flaps, yeah, it needed a SQL. It needed a real database. It needed to be able to do complex aggregations and querying, and it worked really well because it didn't own that data, right? It's like the owner of the data was still flyD, or the central system, which had like account data, right? It had the account models, the network models, organization models. But we would, through corrosion, we could share that state with every flap, so that it didn't have to have its own store. That could have changed, since I left. I doubt it, because again, flaps is very easy to operate and scale and manage, because it had no database. It worked really well for that. So
okay.
Yeah.
Well, that brings us to fly-proxy, the last piece of this puzzle. There's a few others, but like the last critical piece, I think, of this puzzle. Because if fly-proxy doesn't work, as we said, like everything like traffic is not going anywhere. Users are unhappy. That's, I think, the first component that users would notice if there's an issue with.
Absolutely. Yeah. fly-proxy, I am always, it's like it was a marvel to see fly-proxy, the design of it, how it was, how it just managed connections, and it was really cool to see. Because I would occasionally, I know it irritates Jerome, and I think it's okay to say this. I would every now and then make comments about like, hey, you could probably do that in Envoy, knowing that like he'd be like, absolutely not. You can. I know he's right. Like you, if you could, it would be pointless because it would be
For
easier to just write your own proxy.
for everyone listening to this, what is fly-proxy written in?
Fly-proxy is written in Rust. So Jerome is big Rust proponent. Ultimately, when they were basically choosing, it's like, okay, they didn't want to write it in C++ because they're just the talent. Like that's a language that I think you have to have a pretty deep level of knowledge in. But Jerome had been learning Rust and using Rust for a while. For me, it doesn't make sense to write something like that in Go, even though I know that those exist. Just because you do have the garbage collection, you have potential issues with memory and data safety. And I think Rust has done a really good job with its language, the design of the language, obviously the performance, and it just made a lot of sense. And the biggest one is like, yeah, it could easily access like syscalls because it doesn't have a lot of overhead for that. And so fly proxy, the way it did work, and it used to have the state of everything almost at all times, every proxy, right? Obviously, that was very inefficient, but it was also sort of easier to reason about, right? Again, it's like if you think about the simplicity of things, it's like, okay, when a fly proxy in London needs to send a request to a machine in another region, it doesn't it just already has that information and it knows where that machine is, and it knows how to connect, basically to send the request there. I want to say a little over a year ago, definitely over a year, maybe a year and a half, the proxy team was like, okay, we need to improve the reliability of the proxy and some of the performance characteristics of it. More importantly, like if a bad record went into corrosion, so fly proxy also used corrosion for its state. But if a bad record went into corrosion, it could potentially poison every proxy. And the way that would come up would be like when the proxy was updating its state, in-memory state from like corrosion, it could like lock it. And by locking it, that means like could potentially cause all proxies to lock up and not be able to process requests. I think that happened a couple times. After it happened twice, it was like, okay, fool me twice. Third time, it's like, we're changing this. And so that team has been doing a really ambitious goal of making the proxies more regional by default, but it can obviously still route requests globally. So again, it's like, from a reliability standpoint, it would be if the proxy in a region happened to, have an issue due to data inconsistencies or a bug due to the data, it would only affect that one region. And I think that was always the one big goal of Fly is like, we want outages and incidents to be regionalized. Again, you go back to like the machines and like why we didn't want Nomad. If Nomad had an issue, that impacted everything. If we ran them regionally, yeah, that would be one way to do it. But we decided like, okay, we don't even want that regional component. The proxy is probably one of the, it easily was the most critical piece of all of Fly because, yeah, the whole point of running an app is to send a request to it for the, if it's that kind of app. And so that team was doing some really great work to try to figure out how can we make it such that like the corrosion system, I think they ended up with like 2 corrosion systems. There's like a regional corrosion, and then there's still the global one because flaps at the time, there was a lot of issues that I felt like was going to make flaps too complicated to try to make it just have region data. I think they'll get there to make that even better as well. But they focused on the proxy because that was the more critical piece. And so now the proxy, I think it lazily loads data. So it doesn't try to load every machine in the region. I mean, maybe it does it in the region, but then also if it doesn't have the record, it has a way to lazily load that. So you do have, there's a performance cost with doing that to the latency of the request. But I believe that ultimately, what they saw was like loading it from SQLite on demand was marginal overall. I mean, obviously, you're talking about microseconds versus potentially a few milliseconds, but it made sense to have that trade-off when it came to the reliability of the proxy and not having these global outages anymore. Because if flyD could cause a global outage, sort of. It's like if we pushed a bug, and it's like flyD, like couldn't start, like failed to boot. It could affect systems, but like if machines were already running, they continued running and requests would go to them. That was the other thing is like flyD wasn't in the critical path of like processing an HTTP or a TCP request. It was out of band from that for the most part. The proxy, it had to work and it had to work all the time. And if it did fail, it needed to fail on as small of scale as possible. I don't know that they'll ever open source fly-proxy. It's very fly specific, but there's some really interesting, like just engineering design that have been put into the proxy. It's probably the oldest running piece of running software there, if I had to guess.
Yeah.
Like I think the very first version of the proxy, it wasn't. I don't think it was written in Rust. I think it was written in something else. But then they were like, no, that's not going to work, and so they rewrote it in Rust, and it is what it is today. But again, even the proxy, like without corrosion, like how would the proxy get its data? It would have had to do like a network call, right, to like get information, and that just adds more potential for issues. So again, corrosion was like, I think corrosion is a piece of software that a lot of companies, if they could understand it and deploy it, it could change how they build and operate their system, because it definitely changed how like Fly was able to do things at a global scale.
So a lot of appreciation to everybody that open sources software that is battle tested, like corrosion.
Yes.
That is so instrumental and fundamental to what a company does. There are so many learnings there in that piece of software. I know that when we exchanged messages, obviously before the recording, you were saying that there's a few open source components that are interesting, some just to look at. They maybe can't be used as they are. You mentioned something about FSM, and I'm excited to look at FSM. But before we do that, I'm wondering if there's any other components, open source components, that you think would be worth looking at in this context, in the context of operating a global platform, machines, cloud infrastructure, something large scale that has been proven for years and years, that there's some nice things to learn from, if nothing else.
Yeah, I think I'm hopeful that Fly will open source Pilot, the new the init that is used in machines now, or in most machines now. I would think the original version of Pilot was dead simple, right? It was a base init system, and it morphed into being an init system that was like CRI compliant, right? Like it is a container runtime implementation in an init. And for a lot of companies that are wanting to run workloads, but they need to do this multi-tenancy, having a system like Pilot and being able to build from that would be pretty interesting to see. So I'm hopeful that they'll open source that. I don't know, proxy, it is very Fly specific, but I bet that it could be useful just to see the inner workings of it. I don't know that it would, anybody could just pick it up and run it, I would think. And then, so the FSM one, so Fly did end up open sourcing the FSM, even though it's like an internal component of flyD. My understanding is that they open sourced it for the sole purpose for hiring, which, I'm not surprised by the way Fly did hiring. It was very like, we're going to give you a problem that we have. We're not going to give you this like nebulous problem based on like, engineering designs. It's like, no, this is like something that we need to figure out, or this is something we have that like we need to change or make better. And so they open sourced the FSM code. It's probably, again, I don't know if it's usable as is. It might be. I did check it out earlier this week to see like, yeah, you can use it technically. It's got some interesting things to it that basically I learned from my time working with MongoHQ Compose.io. We had an orchestration system that was written in Ruby. So it had this idea of like recipes. So a recipe would be like create Mongo or like create Redis. And you would have the recipe and you'd say like, all right, I need, 3 data containers, two proxy containers and then like an ancillary container. And so that orchestration system would take that recipe and then it would build operations. An operation is basically like, I need to run this command on this remote host, get the output, and then go to the next operation. And there were some interesting things that we built there where like, when you think about like when we were orchestrating like MongoDB, when you needed to upgrade it, you wanted to have a very seamless upgrade experience. And to do that, you had to, the current primary had to be like basically be demoted. And so what we do is we would, the orchestrator didn't know who the leader was. And so when it built these operations to do this upgrade, it would be like, hey, I need you to upgrade. And it was like, hey, I'm currently the leader or the primary. I'm going to defer. And it would actually take those operations and move them to the end for that node. And then it would move to the next one. And then once it got to the current leader, it would be like, hey, I legit need you to like be updated now. And it would kind of do that process. So there was that one. And then at HashiCorp, I used Cadence. So Cadence is a deterministic workflow engine. The predecessor to that, I believe, was AWS Step Functions. So like the individuals that worked on that product, and then they built Cadence while at Uber. And then since then, they've started their own company, Temporal, which is, I think it's a great piece of technology. It is a useful tool to have in your architectural design when, if you need that type of thing. So I'd done a few different versions of this over time. And then when I wanted to build, when I got to Fly and was going to build flyD, I was like, okay, I want deterministic execution. I don't want the complexity of having like a cadence. I don't want a central system. Like this should all be, it's got to be on host. So how can I like take some of the good pieces that I liked of like deterministic execution and build a very simple, library. The original version of the FSM is awful. Like it's still running today, like, but it works. It's not one that I was proud of, though, I would say, because it was like, I really just needed to get something working. I didn't think about like the API of building the FSM. And more importantly, it's like, once you have a state machine running, when you deploy new code, what happens to that state? Like if you add a new transition or you delete a transition, how does the system supposed to respond to that? So the original FSM in a lot of ways was terribly designed just from like the user, how you actually, use it. And so the V2 of that, I started working on, it was like, I think it was about 3 years ago. And I just kind of slowly worked on it and tried to make it a good API, a good experience to use. Where it ended up is it's still not where I would want it. Like there's some small things that I would want to change to make better. But ultimately, I think it does a really good job for what it was designed to do. If I think about in what environments would this be useful, it's probably a pretty small subset, right? It's like it doesn't do any like it's only for like you have to believe that whatever process you're running is going to always be there, and if it goes away, like nothing else is going to come and like take its place, right? So there's no like replication of data or like gossiping between it's just like it's a simple library. You can define sort of a state machine. It's a very simple state machine. You have a start and an end. There's no branching. There's no like jumping, from one transition back to an early run or skipping. You can't really skip transitions either. You can, but it's a little different. Yeah, I actually think I got most of it right in the V2, and so I'm actually I'm somewhat proud of that. It is open source and on super GitHub. It's interesting.
Would you like us to look at it?
Yeah,
share
we
a
can
screen and just like
sure.
look at the code, just to see what this means in practice.
So this is the GitHub repo. It is, like you see, it's used for hiring clearly because all of the tests have been removed. The README is empty. There's no like working examples or anything like that. And that is because, they are using it as a tool to basically see like, how would you approach maintaining something like this? Because it is a core part of flyD right now. So I was playing around with a few things this week. Take a look at it. So I was also playing with the machines API again. But what I did was I just cloned the repo into an internal package and deleted the Git and the Go mod and everything. So it's basically like an internal package to this in case I needed to change anything. I don't think I ended up needing to do that. The way it starts is you have to initialize the FSM. This is where you're basically telling it where you want to store the state,
Yep.
and you get back this FSM manager, and it's with this manager that you can then register FSMs. So down here is where we are saying, all right, we want to register an FSM.
Okay.
The way it works is every FSM, you basically have like an input and an output, or like a request and a reply type of model. And in this case, I just said my request is a string and my response is a string. And then it uses sort of the builder pattern in Go, and that you first register it. When you register it, you provide it that FSM manager, and then you give it an action. In this case,
Right.
the action is demo. At Fly, it was like create machine, create volume, stop machine, start machine. So those were the actions. When you register it, you're going to get back a start function to initiate an instance of this FSM. But you also have the resume function that it exposed, and that was basically like when you shut down and you're starting back up. It's like you want to decide maybe when you resume, because there could be dependencies within your FSMs that you need to make sure are like working and online before you resume them. So from there, then you say, all right, you have a start again. So it's pretty simple. It's you have a start transition, and then you'll have an end one. All of them have a name. It's just a string, and then you provide it a function, and in that function, it's going to give you a context. It's going to give you a request object, which gives you access to the data passed in as the request, and all you're doing is you're returning a response optionally, and then an error. And so from within this one, all I have it doing is basically it's going to run after a certain amount of time, and then it's going to move to the next one. And then within the second one, it's really the same sort of deal. And then you say end, and then you build it. And so that gives you like these functions that you can invoke. So the start, the to, and the end, they all have a variadic options. Because one thing that we learned, or I learned, we learned with the original FSM is it's like sometimes you don't want to have a bunch you want the transitions to be very small and scoped. Like it should only do one thing, and then if it does it, it's successful. And if it doesn't, it returns. But sometimes you might need to like do something before running the transition, and maybe you want to do it before running it like every time. And so it has this concept of like interceptors. So it's basically middleware, right? Before you run the transition, I want you to run a bunch of middleware. It also, we found that sometimes we needed to, when we started an FSM or resumed it, we need to always initialize something, whether that's like we wanted to give it access to like a database connection or something like that. And so there's an initializer that will always run when the FSM starts or resumes. And then you have finalizers. So like, let's say the FSM failed and it wasn't going to finish. We needed to clean stuff up, right? Maybe we've downloaded image, or we've created a bunch of directories that we now want to clean up. You can pass a finalizer function to end. And so regardless of whether or not the FSM finishes to the end, or if it, errors out and at a, critical error, we'll always run these finalizers. So yes, it's pretty simple. And I say it's simple, maybe it's not. To this point, you
looks very straightforward. I mean,
Okay.
that's like logically, it's
Right.
very easy to follow, and
Okay.
everything makes sense. And I think, as you mentioned, like the branching isn't there, like this
Right.
and that. So once you introduce that, things start becoming, because you need to hold all those branches in your head.
Right.
The way it is laid out right now, again, it's very straightforward, like almost like sequential, with a couple of, like as you mentioned, the initializers, the finalizers, and the interceptors, and they all make sense.
Right. Okay. Great. So yeah, so you'd have this. Typically, what you do, you might have to set up some other stuff. In this case, we're just going to immediately call resume, but it doesn't block. Resume will just be like, all right, I'm going to start back I'm going to make sure I want to start them all back up, and then I'm going to return. I'm not going to wait for them to finish. But then this FSM manager, it has a few functions on it. One of them is active. So you can say like, is this FSM already active based on an ID? So when you run an FSM, all of them have to have an ID. The ID is unique per action. So in this case, the action is demo. I'm saying for this one, is there one active? And if there is, it provides a wait by ID feature. So you can basically say like, you can wait for it. Actually, okay, so the ID is across, you can have multiple FSMs running with the same ID, but you can't have one action with the same ID, because like you might be able to want to do things like in parallel. So one thing we did with this was like, when you're creating a machine, we might need to go and pull images for like multiple images for a machine. We can do that in parallel. And so it would fire off like an FSM to pull the image based on the machine config. And the ID was typically just like the machine version, but they were all the same. So you could fire those off and then wait for them to complete. So you can basically say, I want to wait. If there is one running, let's wait for it. If there's not one running, we'll just go ahead and call start. We pass in an ID. We build this new request object again, and the parameters to that is going to be this hello string, and then the result is result. We're going to log whether it worked, and then we're going to wait to see if it completed. So if I run this real quick, we'll see. All right, so it's starting up. It's running the first one. It's sleeping for like 10 seconds before I move to the second one. And then I'm going to control C on that second one. So it's running the second one. All right, so I'm going to control C. So the idea is like, okay, we need to like deploy flyD or something like that. And so flyD is now stopped. We're updating the code. We're starting it back up. And so we'll just start flyD back up. And so you see what it did is it said, it's iterating the events. It restarted it. So right here, this run version, it's a ULID. So that is unique for this instance of the FSM. And so you see we logged like FSM is already running. It's going to wait for it to finish. So it ran the second, it done running the second, completed, and we saw we're done waiting for that one, cleaned it up from the store, we're starting another one again, right? And so it's basically went through that whole process because we started a second one. So one thing that's interesting that we learned as well that I'll try to, so I'm going to run it one more time and I'm going to stop it on this first one. So let's say we wanted to add another transition or delete one. That could wreak havoc, right? Because it's like, okay, it was running it and then either you're resuming back with first and first doesn't exist anymore, or you've now like added another one. So what I'm going to do now is just for simplicity, I'm going to say second is now, I'm going to add a third, but the running, when we started that FSM, third didn't exist. And so if I remember correctly, what it does is when it starts an FSM, it snapshots all of the transitions for that FSM, and that's all it's going to run. And so let's say if we now...
Before we run it, if you go back, you will want to modify the logs as well to be third because it'll be confusing.
Yes, it will. So, and there's actually a better way to do this. I'm going to say log F, log S. The request has this run object, which gives you access to things like the current state, which is the string. So I'm going to make that.
I think I'm missing the same thing, the line above. Missing an S after the %. The line above.
Yep. Okay. So I think that'll do it. So we shouldn't actually see running third state when we start this one back up, because when we started originally,
didn't have the third state.
It didn't have the third state, right? So it went back to running the first, because that's where that's where it was when we controlled C at the first time. Now it's running the second one. And this one should complete, I think 10 seconds. But now it should be finished, right? So it finished. It didn't run that third step, but now we're running it again. And this time we should see running first, running second, running third. So that let us basically, we can modify an active FSM, or we can basically, deploy new code, change the transition. We can add one. Here it is. All right, so we're running third now. It's not going to get run on that resume one, but it is now going to run for this newly created one. So there was one other thing that was actually very interesting. I'm going to run it again, but this time I'm going to stop it when it's on the second transition. So sometimes we would add a transition and then ended up we'd be like, okay, we've moved the code, or we no longer need this transition. Like it no longer needs to do that work, right? So
Yeah.
we're going to stop it on that second transition, and now we're going to delete it. Right. Second
Right.
transition doesn't exist. In the original FSM, you had to like leave that transition in place and basically like no op it. And so you had to do like multiple code deploys. So right, you would deploy the code with the no op, and then you later on you'd have to make sure that all running FSMs for that action have finished before you could then go and like clean up the code. And that was just obviously a bit of a nightmare to manage. So now if we start it back, what we'll see is like, okay, the transition didn't exist. So I'm just going to skip it. And it goes
Yeah.
straight to the third. So that was the other big one where it was like, okay, we need to be able to like deploy these, change these transitions, remove them. We can even reorder them technically, and it would all still work. But yeah, so that was one of the real big things that we learned there was being able to modify the FSMs, and
Yeah.
the ones that are actively running will just continue running. So yes, that was I think that was probably one of the more interesting pieces of that. I think the database, we could probably crack open the database with it not running and look at it. But basically, yeah, what it would do would be when you start the FSM, it snapshots all of the transitions and it persists that in the database. And then so when you're resuming it, what it's going to do is, okay, you've now registered this, FSM again. Your transitions are different. I'm going to ignore the ones that didn't exist previously, and if you've deleted it, I'm just going to turn it into a no-op transition for you. So yeah, so that was quick little demo.
Yeah,
Didn't
this is really
show too
cool.
much,
Wow.
but
Well, first of all, thank you very much because this demo had to be written, so it didn't exist, right? When we started talking,
right, I appreciate it. Yeah,
so I'm sure it must have brought back some memories. The
it did.
fact
Yeah, it did.
that this works just as well as it did, like when you stopped working with it and you just left it like in that state, it's so nice to see. It's almost like you come back to something that you've poured so many months of thoughts and
Yeah,
effort and seeing it work so well. It hasn't been that long, but I can imagine that even after a few years, this will just work, and many good decisions and hard-earned lessons have been implemented in a way. It's just simple. And even to me, this is the first time I'm seeing it. I haven't looked at the code. I know it was out there, but I just wanted to see like that first experience, and it just made sense. That is a
thank you.
good test to know, like someone that hasn't seen it before. If you show
Yeah,
it to them, will they get it? And if they do,
yeah,
then I think you've ticked one more very important box, which is onboarding new people,
I
people that
appreciate that.
will pick it up. So this
Yeah,
is really nice.
thank you.
Okay.
Yeah, so and I'll say one other thing that was when I forgot when it was, but like at one point, so the FSM, I think it's instrumented with open telemetry for both tracing and spans that has logging as well. But what was interesting was like I think it was Ben Johnson went and built some dashboards for the FSM, and you could just see like the amount of things running at any given time, and it was in many ways you'd look at it and be like it's just a lot of stuff happening in the system at once, and having a
Yeah,
dashboard to kind of visualize that and just see things working
that's so
all
nice.
throughout the day was really
Oh,
cool to
wow.
see.
Oh, I wish we had more time to look
Yeah,
into that. Not today, for
yeah,
sure. But I just love like that proper observability in which you don't even need to read the code. You just hook it up and you understand what is happening at a very deep level. And
hmm
it's like conceptually, you can start forming ideas about how this thing is put together, and the code just confirms it, confirms what you observe from the outside. It's like that black box approach.
yeah,
And having that's just
absolutely.
like another level of refinement. So you really took your time and you've done a
Thanks.
great
Yeah,
job. So yeah,
tracing to me was important because, like, again, it's a black box, and I like a lot of the tracing tools. They'll give you that nice like trace waterfall, like the
yeah,
span waterfall view, and you can actually see like, oh, this is what the system did, and we used it a good bit to be like, okay, this is where we're spending a lot of time. This aired when it shouldn't have aired, or like we're seeing errors that we wouldn't expect to see.
Yeah.
And again, that goes back to almost like the SQLite and the BoltDB. It's like, okay, if you can't inspect the running system, and
Yeah.
I didn't want people wasting time trying to like stare at logs. To me, like we had metrics that could give you like quick high level health, and then you could look at every, almost every running FSM with the traces to see like what was
Yeah.
going on and how did it actually work.
Yeah. This, in my mind, just makes the code or system be like a fractal, in that you're just like taking a different perspective on the same thing, and it just allows you to understand something differently. And it's almost like it allows you to double check your assumptions or how you think
Yes.
the thing works, but from what this is just process.
Absolutely. Yeah,
It
yeah.
really
Because
is.
it's not if you didn't write the software, you probably don't really know how it works. And
Exactly.
so, yeah,
Yeah.
you need observability is critical for being able to like, yeah,
Yeah.
pick up software that someone else has been written and be able to manage it, or just be able
Yeah.
to support a running system like that.
But even taking a step back, right? Like, how do you take a step back from what you've built? I mean, you're in the weeds, great, but now you want a high level perspective. Okay,
Yeah.
so let's see how the system works together. Does
Hmm.
it make sense?
Yeah.
And a waterfall view just gives you that extra perspective. From this conversation, this was one of my very important takeaways. Like, there's so many layers to good software, and if you approach this in the right way, you can build some crazy reliable systems that
Hmm.
stand the test of time. So that is my takeaway, but I'm very curious about your takeaway for those that stuck with us all the way to the end.
Yeah. Probably from the outside as a customer of Fly, hopefully it looks like a very simple system. But when we think about like everything it takes, all the software that's been written and it's been constantly maintained by some very talented people, what all it takes to make that experience that simple is just like it's pretty massive, right? And then to do it reliably, as I think they've really been able to do for the last couple of years now, really. Yeah, I think for me, it's just like appreciative of having been able to play a part in making what I would say cloud infrastructure easy again. Yeah, because we didn't even get into things like DNS, the WireGuard network mesh. Like there were just so many
The
really
logs, the
the log,
metrics,
yeah, everything that was really
what
done to
makes the
make.
dashboard behind me possible.
Okay, yeah, right.
Oh, that's what
That's
that
right.
is, by the way.
Yep. Oh, that's great.
But yeah,
That's great. But yeah, so like all these things that like you have like a pretty the company itself is still not, it's not large, and there's been a lot of people that have invested this kind of time over the years to try to give that easy, seamless experience. Yeah, I think my takeaway is just how I'm just grateful to been able to have had an opportunity to kind of help build it.
well, JP, I really enjoy this. Thank you very much for giving me an extra layer of understanding to how this very complex but beautiful piece of tech is coming together. Thank you for your contribution once again, and allowing me to build something that would not have been possible without Fly. And I'm referring in this case to Pipely, the CDN. The listeners will know about that story, so I'm not going to dig into it too much. But it would not have been possible without Fly. And the ease, nothing like it. So thank you very much.
I really appreciate that. That's great to hear. Yeah, thanks for having me. This was great. It's been a while since I've been able to kind of just talk tech like that. So it's
It
fun.
was my pleasure. Thank you very
Thanks so
much.
much. Thanks.